Okay, now I'm going to ask you to take a look at the diagram that's up on the board. You don't probably need to copy it down yet. You probably honestly just need to think and look at it. Make sure that you can see, though, the three parts of that diagram. There's a function. The function's in white. It's probably like a parabola. There is a red dashed line that's connecting points A and B. There's a red dashed line connecting A and B. Make sure you can see the blue line. There's a blue line. I'm not going to say too much more about it, but there's a blue line that is, it's at a point C. I forgot to mark that, but I'll put that down. Okay, so we have kind of three parts to that diagram. Now, what I'm going to ask you to do is, using that diagram and hopefully some good thinking, is to see if you can figure out the mean value theorem. Now, if you're like, what's the mean value theorem? Well, that's the idea. You don't know what it is, but all it's going to take you doing is making basically an intelligent connection between some words and phrases. So I'm going to give you I think it's like 4 words, phrases, and you're just going to try to make a sentence out of them. But it's a sentence that relates to that diagram. Okay, so by the way, if you do this well, you will have figured out the mean value theorem. Don't Google mean value theorem. That's not what I want you to do. Instead, I want you to try to use these, I guess it's 5 words, phrases. How can you connect them using this diagram? We'll change that to 0 to 3 so it matches. And here's your point C. Again, you're trying to make an intelligent statement. You're trying to make a statement that connects those words according to the diagram. You could use the word slope twice. Every other word or phrase you're trying to use just once. Hopefully you're not getting tired of maybe reading or seeing the answers, but they do start to sound the same, which that's good. How do I thought there was a way to freeze this. See if we can, I'll just use the old freeze button on here. Okay, now keep in mind that these statements, and I'm going to freeze it on one that kind of ties it up real nice. These statements, they are the mean value theorem. Okay, I'm going to stop it on this one. Not that the other ones are wrong, but this kind of tidies it up in some of the simplest way. I saw a few of you did contribute this. Somebody's feeling really good right now. The only thing I would add to this, and I didn't expect anyone to put it down, is the word always. That's why it's a theorem. This will always be true. What will always be true? It will always be true that the slope of the tangent at some point, or in here it says at the point, but at some point, will be parallel to the slope of the secant. Okay, for every interval, in fact, I thought it was going to be a to b. I forgot I made it 0 to 3. But for any interval a to b, you will always be able to have a point where the slope of the tangent is parallel to the slope of the secant. Okay, it's actually quite an intriguing idea. It's also kind of simple because basically what you're saying is that you're always going to have these two lines able to be parallel. Okay, now we call that the mean value theorem. I like what you guys wrote. I don't want to suddenly say, here's the right answer. I'm certainly going to share with you the same answer if you want to copy that, but please understand that most of you are writing down something very similar to what you already said, which is good. But I know students like to know what's the right answer. Again, the right answer is what you wrote down, or you can summarize it with this. And again, that word always is actually what makes it a theorem, knowing that this will always happen. Now, what we usually do with this, which should be the next kind of logical question, what am I going to do with this? Well, we prove it. And the way that we prove it is by actually finding the point. We find the place where these two slopes are the same. Now, that little phrase that I said, where the slopes are the same, kind of summarizes this whole theorem, because we're basically looking for two slopes that are going to be the same, and we just want to figure out where this happens. Okay, let's do that. Let's do that for this problem. I need to give you some more numbers. Basically, the function needs to take shape. Let's call it 1.5x squared plus x. So it was a parabola. Now that I have the function, I'm able to find these slopes. Okay, and again, that's really what this kind of boils down to, two slopes. Okay, now the slope of the secant, if you're like most students, it'll be the one that kind of gives you, I don't want to say the most trouble, but kind of makes you pause a little more, because the slope of the secant is actually not a calculus idea. The slope of the secant is just a good old rise over run, a good old change in y over change in x. I'm sure in algebra class, you remember working out statements where you did like f of 3 minus f of 0, and then 3 minus 0. But as you write that down today, make sure that you realize, okay, that's just some y values and some x values. We're just subtracting some y values and x values. Okay, but again, make sure you're thinking, okay, f of 3, f of 0. You got to plug it into your function. Again, kind of basic algebra ideas, but you have to think like that. So you can plug it in mentally, you can write it out. Just make sure you realize that we're squaring the number 3 as well as adding 3, and out pops a y value. Okay, it actually comes out to be 16.5. F of 0 is easy to do. Just plug a 0 into that function and you end up with 0. All right, so the change in y over the change in x is really the division of 16.5 and 3, and we get a nice little slope of the secant. Get the slope of the secant. How about the slope of the tangent? How about the slope of the tangent? Well, now that should make you smile a little bit. As a calculus student, that's what you've been studying for the last many months. Okay, and it's kind of fitting that it ends up being one of the last things that we do in this first half of the year. So the slope of the tangent, okay, remember our little chant? Well, I guess it would be backwards here. When I say tangent, you say, well, actually, maybe we should say it forward, but I'll give the answer. When I say derivative, you say slope. It's a derivative. Okay, it's a derivative. So we're going to do the derivative. It's kind of been what we've been doing. Please understand when you do it that you're finding or you're working towards the slope of the tangent. Okay, nice little derivative of 1/2 x squared is 3x plus 1. Now, this is a little bit of a part in this problem where you realize, oh, wait a minute. I don't know what this slope, I don't have a number to plug in here, do I? No, I don't have a number to plug in. Instead, I have something to set it equal to. Because if you think about what you guys said and what I said up here, we're trying to make the two slopes the same. We're trying to make the two slopes the same. So basically, we're going to find C, but I don't want to make it too complicated. All we're really going to do is make our two slopes equal. And so that means 3x plus 1 has to equal 5.5. And look, you're solving for C or x. Okay, you're solving for C, otherwise known as x. All right, subtract 1, divide by 3, bada bing, bada bang, and you get x equals 1.5. Okay, now the theorem has been proven. The reason it's been proven is because we found the point. You say, well, wouldn't you always? Yes, actually, we always would be able to find the point, because there's always going to be a point where the two slopes are equal. There's always going to be a point where the two slopes are equal. Okay, we call that the mean value theorem. Look at this formula. I didn't want to show it to you first, but Now I want to show to you now, do you realize that this summarizes this whole process? But it's kind of neat because it can be written with some simple math notation. F prime of C. F prime of C. A student like you should be saying, okay, that's the slope of the tangent. That's the slope of the tangent at this point C. And what do we want it to equal? We want it to equal the slope of the secant. If you want to write those words, if it helps, the left side is the slope of the tangent and the right side is the slope of the secant. Basically, we're solving for C. Okay, now, sometimes kiddos will more sooner than later say, well, is it always just like halfway in between? You know, let's be honest, halfway between 0 and 3 is 1.5. Is it always halfway? I don't know. Let's find out through another problem. One thing's for sure, that it's always between, but is it going to be halfway between? And to kind of research that a little more, it's usually helpful to come up with a different kind of function. How about like a inverse tangent? Now, it doesn't get much different than that. An inverse tangent by the way, this is kind of like what you would be given. You would be given a function and an interval. And you would be given a set of instructions. This is basically the fancy way to say find C. But it usually will say like satisfy the mean value theorem. So when you see that phrase, satisfy the mean value theorem, it means find C. Basically prove that everything can happen. Sometimes people are a little more eager to, even though we only did one problem, but to kind of think through this, because it is kind of just like a little process. Like I promised, you can do the same thing that I did in that other problem. I'll give you a little time to think about it before I just do it. Okay, don't be scared to use a calculator. There is a calculator component to this, because if you're right now trying to figure out f of b minus f of a all over b minus a, yeah, you're going to need to pop that in a calculator. That's fine. This is the slope of the secant. Don't worry, even though it's like an inverse tangent, you're still going to be able to plug in 5. Make sure your calculator's in radians. Okay, and it does kind of just spit out a decimal. It's fine. You know, usually 3 decimal places is a little better than 2, so we can round to 3 decimal places. For some reason, I only have 2 decimals there. But make sure you understand that 0.275, that's a slope. Okay, that's a slope. What are you going to do with it? What are you going to do with it? You have to now be thinking about setting it equal to a derivative. Okay, we got to get this derivative involved. Yes, I'm trying to get you to remember the derivative of inverse tangent. It's interesting, you'll need this derivative for the second half of the year. And so if it slipped your mind, it doesn't hurt to look it back up. Okay, but we don't want to forget, it's actually a rule. It's a rule. And that's it. There's really nothing that I have to do to adapt the rule. There's no chain rule. There's no extra x's. It's just point blank a rule. Did you find it? It's 1 over 1 plus x squared. That derivative, just trust me, and that's kind of why I'm doing this problem. Again, it's going to reappear quite a bit. It's going to reappear backwards. As I've been kind of telling you, that's what the second half of the year will be. But don't worry, we'll get there. Can you think through the rest of this problem? You have to do something with the two slopes that we found. Okay, and that's something which it'll be this way every time. That's why I'm just giving you guys time and just think about this, because all you're going to do is set them equal. You're basically making the tangent equal the secant. You're making the tangent equal the secant. And when you make that happen, you sort of force this c value or x value. Okay, you force the ability to find this. Sometimes, and it's okay, we're all trying to learn along here. Sometimes people need a little refresher on the algebra. Try to keep the algebra simple. Basically, the denominator wants to get multiplied over here, and this 275, it wants to get divided over here. It's like a swap. Okay, so we don't want this 1 plus x squared in the denominator. We want it kind of in a more of a numerator shape, but this 275 gets divided over here, so 1 divided by 275. I know it's a little bit rounded because we rounded prior. That's okay. If you're working with 3 decimals, it's fine. But obviously, I'll subtract 2 and then take the square root. I'll take the square root of 263. Subtract 1, take the square root. Now, I know you've heard the algebra teacher say it before, but he's going to say it again. Whenever you take the square root, you get a plus or minus. That actually brings up kind of an interesting final observation about this problem. If we were going to sketch this, we would have to sketch inverse tangent. I'm not going to go back through the trigonometry, but inverse tangent would be kind of like a sideways tangent. And there would be a secant slope. There would be a secant that was between 0 and 5. Looks a little crooked, but there it is. And apparently at 1.537, even though it's just a sketch, doesn't it kind of look like that? It looks like that it's not in the middle. Yeah, we want that tangent line to be down here so it can be parallel. Now, there's only one answer. There's only one answer because there's only an interval from 0 to 5. So it turns out that even though we were smart with the plus or minus, we don't need the minus. But since we have a moment here, if you continue to think about parallel lines, you would say that the minus would make sense. In other words, the minus version would still be parallel. It just doesn't fit our answer because our answer is only from 0 to 5. Okay? But it works every time. It works every time. By the way, when you guys make I'll just tell you. Hey, one more thing to say about this. It might have been nice to say it before the bell, but if you're ready to kind of re-engage. And I purposely have both these problems for you guys to look at because, yes, you'll do what we did. You'll find X or find C, but then you will always support what you found with a sketch. Okay, you will always support one of these mean value theorems with a sketch. So what will the sketch be? It'll be the sketch of the function. It'll be the sketch of the two lines, the secant and the tangent. And then it would be the C value, kind of like making sense. You can label it if you want. Kind of like I was pointing out over here, it makes sense that this C value is not halfway in between. It's not halfway in between. In fact, it's only at 1.5, so that it's able to have the right slope. Okay, if it was halfway in between, then it would be tilted more and the slopes wouldn't be parallel. By the way, for this sketch, we would not be adding in this extra piece. I was simply showing you that the plus or minus would make sense if we were going to also be on the other side of 0. All right, so you always make a sketch, a function, a couple parallel lines, and then point C, and that makes for a nice, tidy mean value theorem problem.